Hi everyone, so welcome back, and I want to thank the school for the opportunity to present, and also congratulate on the recent launch. It's absolutely fantastic and deserves a lot of applause. So yeah, here today really just to talk a little bit about Gilmour. We only have a few minutes, I guess, for each session, so I'll try and keep it pretty brief. But we've actually done or had quite a lot of progress in the last 18 months in specific. And it's exciting because I got to attend this conference back in 2015. At that stage, I was very new with the organisation, and we just started building the foundation for testing some of our propulsion and some of our plans. And we've now since done that, and we've also had a launch, as you'll see, last year, and we got to actually flight test some of our work. So that puts us in a fairly unique position as being pretty much the first private enterprise in Australia that's launched a rocket. So just a brief agenda. Originally this presentation was a little bit bigger, and I trimmed it right down because of the time constraints. So it's just a brief introduction, which I've covered now in talking. Our mission statement, basically, some key milestones that we've had, which I've got in a video format, so I'll just show you some of our tests and what we've achieved today. A bit of a focus on our technology and what it is that we've actually, some of the breakthroughs we've made that are going to change and revolutionise the space access and bring the cost down significantly, we believe. I'm going to unveil our concept for the Eris launch vehicle, which will be servicing, or as our entry into small satellite launching, and just a quick summary with regard to contact with us online, etc. So our mission is to develop disruptive propulsion and launch vehicle technologies and help spur along a revolution in space access. That's really what we're targeting with what we're doing. This is a picture of our demonstration vehicle that we launched in Westmar in Queensland. Basically, we operated from a launch site in there, which is run by the State Rocketry Group, and it's run on one of the largest wheat farms in the whole country. And we actually have CASA clearance to launch vehicles to about 30 kilometres of altitude from that site. So I have a video here that just shows some of our progress and what Gilmour's been engaged in, and I'll talk you through it a little bit as it goes. But basically the core focus, as we say here, is hybrid rocket research, and I'll talk a little bit about what a hybrid rocket is and where it varies. You can see here some testing and development work that we've done on catalytic materials to work with our hydrogen peroxide. This is a static engine firing one of our smaller motors which we use for the launch. This is the test firing of our target technology, which is using the hydrogen peroxide oxidizer and our in-house developed fuel. And this basically shows the launch that we conducted. So we flew to about 6 kilometres with that launch from Westmar. This is an early concept render of one of our launch vehicle concepts. It's very difficult to see. And part of the business that we're involved in also was developing these high fidelity simulators for space education. And these were associated with a space academy which we opened on the Gold Coast to help with develop opportunities for STEM and interest in science. There was the simulators involved, also static displays and museum pieces. That facility is now being put in sleep mode while we concentrate on what we're doing with the launch vehicles and the rocket program. So this is a Mars rover vehicle that we're involved in with the university in Singapore. It actually collects water from Martian soil using microwaves, and this won several international design awards as well for this project concept. So management has a very strong interest in future Mars exploration, and there's actually a lot of research projects that go on with universities in Queensland looking at Mars habitat, Mars environment. So almost some fairly unique experience. Thank you. So as you can see, yeah, so core to what we're developing and the way we looked at it, I think somebody very rightly in an earlier presentation said that payloads really only comprise about 4% of a rocket's total mass. And the bulk of the rest of the rocket is primarily propulsion. So we basically took the approach that if a real breakthrough is to happen, where we need to come in is look at the propulsion. And some other programs are addressing this by reusability, and they say, okay, well, it's okay still to produce a highly complex form of propulsion that's sensitive and requires a lot of work. We'll just recover it, and this is the way we'll reduce costs. So we went in and looked at how can we develop a technology which is intrinsically simple enough, reliable enough, and safe enough that, and low unit production cost to get us across the line, so that we don't mind throwing it away because it's cheap enough for us to do that. So we focused on hybrid propulsion. If people don't know their rocket propulsion much, hybrid is basically a combination of a liquid fuel rocket and a solid fuel rocket, where usually one of the components is the oxidizer is kept as a liquid, and the fuel will generally be a solid, but sometimes there's an inverse of that. So we went in and we focused on hydrogen peroxide as our oxidizer. There's a lot of reasons we did that, but to keep it brief, essentially its density is one of the biggest ones. So it's a room temperature storable liquid. So we don't have any of the challenges that you normally have associated with working with liquid oxygen or one of the other cryogenic oxidizers. It has far greater, almost double the density of nitrous oxide, which is another candidate that gets used. And it doesn't incur the same high vapor pressures as nitrous oxide, so we can have relatively lightweight tanks to store it in. It's listed as a green propellant. The reason they say that is it decomposes basically into hot oxygen and steam. That's pretty much the byproducts of its decomposition. So it's generally non-toxical. We say here simple ignition. Basically, we are able to catalyze the hydrogen peroxide with a suitable catalyst and yield that oxygen and steam for combustion with the fuel. It gives us a solid state ignition device. So all we have to do is open up one valve, flow the oxidizer through the catalyst, and immediately we've got ignition. We turn it off, it stops. So it gives an infinite amount of restarts and throttle capability in the engine. So solid fuel, this is one area we've pioneered a lot in, and it's been a big traditional barrier. It's stopped hybrids from coming into the market. Essentially, there's a lot of complexity with trying to produce a solid fuel structure that is robust, burns quickly enough so that the maximum amount of volume inside the combustion chamber can be applied to fuel. So that's been one of the big areas. We've developed some specific fuel formulations and a method of production that fully automates that. And that's one of our big breakthroughs at the company. The other area where we've innovated is catalyst materials. We've developed a new set of catalyst materials based on ceramics and a salt formulation of our own that I can't talk about or disclose, but essentially it solves a lot of the issues that have been a traditional hamper to catalyst for peroxides. It's much lighter in weight and much higher in activity per volume, so we can have a physically smaller catalyst device. And then the other area that we've been focusing on is producing structures and methods of manufacturing to bring down the recurrent unit cost of the propulsion. This gives us, in this format, the ability to modularize the propulsion and basically build an ever-expanding capability off one engine development instead of developing multiple engines for each stage. So this gives a quick display of what we've done with the hybrid rocket fuel. I think it's a very valuable, visible display, but this is a previous test of what was considered to be a state-of-the-art fuel using fuels derived from paraffin wax. And as you can see, the combustion's highly unstable. It's pretty visually obvious that it's not performing very well, sputtering and coughing and doing all sorts of things. The advantage to this, though, is that increased regression rate that they're looking for, so that they can physically place more fuel into the same size combustion chamber and have that be easier to manufacture. So there's no complex fuel port geometries required. We've developed a formulation in-house, and this is a test firing of it. As you can see, the comparison, very stable in burning. Okay, and it solved most of the structural issues that appear in these types of motors. The paraffin wax actually tends to have a phenomenon called slumping, and what that is basically the soft wax towards the end of the burn being coughed out of the engine unburned. And it's an undesirable quality of the fuel. It's part of the mechanism of what makes it burn, but it's also undesirable because you could lose many kilograms of fuel in a flight. So we don't have that issue. So far, we're yet to find a con with the development and how we work with it. So, next slide. Okay, so I've only got 2 minutes. So I'll really quickly cover. So this is the ERIS launch vehicle concept. Essentially, we are able, as stated earlier, just by modulating the one engine and producing what we call a common core module with a simple pressure feed system, we're able to yield a whole vehicle from that. As I said, simple, is a common core propulsion module used in each stage. Essentially, this is a group of 4 motors under the one tank and with their own feed system. And the final stage used for orbital insertion is essentially a single motor with a cluster of tanks around the outside of it, but we've developed one motor for the whole vehicle. Okay. This motor that we're looking at is a 45 centimetre diameter motor. We'll be testing that later this year and actually launching that as a suborbital vehicle. So we're on track to look at having a launch capability around 2020, placing stuff in orbit. So we have the ability to do the multiple restarts. Why is this important? Because we can distribute multiple satellites to different orbits from the one vehicle. So if we need to make an orbital plane change, basically we could carry a 50 kilogram sat, deploy that at one altitude, then restart and move to a higher altitude in orbit, or change inclination if required as well. It's designed for mass production, so we're using fully automated processes wherever we can in the design, including 3D printing, which plays a big part in what we do, and also filament winding technology. So this leads to what we call the ERIS launch vehicle. So just a quick overview of our website that's going up. So we're making our official announcement about having suborbital and orbital launch capabilities in these timelines. You can also access us online, where we have an online form to talk to us about your requirements and what you're looking for. Earlier, there's also some indicative pricing there for payloads to orbit. So we're actually committing towards a firm set of prices for delivery of payloads. Okay, so in a nutshell, we're looking at low-cost access to space using low-cost propulsion and structures and modern manufacturing techniques to meet that demand. And from 2021, we're looking at having ERIS commercially available, which will offer a breakthrough in cost responsiveness and lightsat and CubeSat users.
Okay, questions?
Yeah. Where's it being launched from?
We're currently in talks with several different launch site providers, and there's also discussion about access to Kennedy Space Center as well for launches.
There's a question down the front.
So did you manage to get through that 4% rule?
No, look, I mean, that still pretty much holds true. We're not so much concerned about that because, as I said, the focus of the technology is to make the recurring cost of the unit so low that the expendable side of the vehicle doesn't really matter. That's really where we want to get to.
It's my understanding that a pretty substantial cost of the launch vehicle is the guidance system on board. Is there any plan to try and recover that to keep your costs low?
Absolutely. No, we're not really looking at it at the moment. Part of the project that we have with the suborbital demonstration launches is to start qualifying flight processes. Traditionally, some of the barriers have been things like the inertial measurement unit, gyroscopes associated with that, or anything involving strap-down inertial guidance. What we've had is, I guess, in the last 5 to 6 years, is entry of a lot of solid-state sensors in that area. So there's things such as butterfly MEMS gyros that bring the cost of the inertial measurement unit down from tens of thousands of dollars down to $3,500 to $4,000. Also, the ability to couple that, or closely couple that, with a GPS receiver. And now that we're seeing things such as Namaro come onto the market, etc., where we've got a high dynamics capable GPS to augment, we can really bring the cost of that down. So the way we sort of see it is there's good potential for the guidance technology to come down into the thousands of dollars instead of the hundreds of thousands of dollars.
Okay, one more question. Ian.
That roughly 30 grand deal on the Saturday order.
Yes.
By the way, thanks for putting the prices up.
Not a problem.
Okay, thank you.
Okay.